evening, Lamai. Right, let's start the class. Good evening, please. You are here, right? Okay, so we are going to start the unit 2 now, right? The structure and bonding lesson. We'll start the lesson then, right? Structure bonding, the lesson 2. Okay, first of all, let's discuss a bit as an introduction what we are going to learn here with the unit number 2, right? What we are supposed to learn with the unit number 2. Let's discuss a bit and then come up with the lesson, right? Okay, so to start with, I'll say like this. Just think of a water glass. Just think of a water glass. So with this, you will get some idea what you are going to learn now onwards, right? Let's think of a water glass, right? Okay. So with the water glass, right? So what is appearing is water molecules, right? Water molecules. So it's just a water glass. A glass of water. Just write like this. Glass of water. Right? With this, you have water, right? So what kind of situation? If you are to picturize inside a water glass, what are the things appearing? So the water. Water means the H2O molecules. So water means is the liquid state of H2O. So I'll just write like this. The liquid state of H2O is referred to as the water. So like this, right? So if you take a glass of water, you will see some H2O molecules are appearing. Right? H2O molecules are appearing. What details we can discuss with this kind of a picture. So it comes to H2O, the hydrogens are bonded to oxygen. That is how the water molecule is produced. Not bonding oxygens like this, no. It is the H2O is not like this. H2O is not like this. The H2O is like this. So your H2O molecules are with this kind of bonding nature. So you have oxygen atoms at the center and two hydrogens at the corners, right? That is how the H2O molecules are, right? So like this. So you have such H2O molecules. Right? With those the water, the H2Os are produced, right? Like this. This is this kind of structure. So what else we can say? Actually, when it comes to water molecules, it is not like this. It is not like this. It is not with some linear conformation. It is kind of a bent structure. So some shape is there with the water molecule, referred to as the bent shape, not the linear. So you would see that thing is also appearing, right? So these are the things we are going to learn with this lesson. The molecules, their bonding nature, right? Their shapes, their bond angles between the bonds. But the bond angle is 104 for the H2O. These are the major stuff we are going to discuss with this lesson, right? So what else we can think of when regarding this H2O glass, right? So basically one can say these H2O molecules are attached via hydrogen bonding. Via hydrogen bonds, the H2O guys are attached to each other. So this is some another detail. So H2O things are attached, right, to each other via hydrogen bonding between them. So those are some details we can gather from a glass of water. So those are the things we are going to learn with this lesson, right? So at the start, we will discuss about the primary bonds. The primary bonds. What are the primary bonds? So primary bonds means the bonds which connect two atoms. So these are the primary bonds inside a molecule. The bonds which connect atoms inside a molecule. So primary bonds, see, those are primary bonds, see. Right, in a molecule, the atoms are connected via primary bonds, right? Bonds connecting atoms, right? Bonds connecting atoms, right? So electron involvement is there. Electron involvement is there. Right? Those are referred to as primary bonds. With this lesson, we will discuss about primary bonds. In H2O, these bonds are called as covalent bonds, where the two electrons are shared. So when it comes to primary bonds, they are of three types. One type is covalent bond. Right? Covalent bond means when two electrons are shared between two atoms, those are covalent bond. Some other kind of primary bonds are also there. So when it comes to NaCl, you will see the ionic bonds. Ionic bonds. Right? Example with NaCl, Na plus and the Cl minus guys are connected via ionic bonds. The ions are connected via ionic bonds. So that is also kind of a primary bond. And the third kind of primary bond is metallic bond. Metallic bond. So those primary bonds are to be discussed under this topic. In H2O, as primary bonds, you will see the presence of covalent bonds. The covalent bonds are normally denoted with these dashes between two atoms. Right? With the lesson, we are starting up with primary bonds, discussion of primary bonds. Right? At the end, after discussing the covalent bond, ionic bond and the metallic bond, at the end, we will discuss about the secondary bonds. We will discuss about secondary bonds. Secondary bonds. This is simply the right outline of lesson. Right? Secondary bonds means, right, the bonds or the interactions between molecules. Interactions between molecules. Those are referred to as secondary bonds. You see, here also you will see such interactions between the H2O molecules. You see hydrogen bonds are appearing. So hydrogen bond is kind of an example. Interactions between molecules. We also say intermolecular interactions. Intermolecular interactions. Right? Such 5 kinds are to be studied. Right? One such a kind is hydrogen bonds. Few more types are also there. Right? Called as ion dipole interactions and hydrogen bonds or the dipole interactions. So dipole induced dipole interactions, ion induced dipole interactions, and finally London forces. Those things are to be discussed, right, under secondary bonds. So with the secondary bonds, we are going to complete the lesson. So this is just kind of a summary, and this is actually the index or what we are going to study, right? So we'll start with the primary bonds, and with the covalent bonds we are going to start, right? Actually with this lesson, if you are thinking of questions to be asked in your A-level papers, right? So actually 70% of this lesson is about the covalent bonds and the covalent molecules. 70% of this lesson is about the covalent bonds and the covalent molecules. The rest of the 30% belongs to these. Rest of the 30% belongs to these. Sorry, I'll put it here. Rest of the 30% belongs to these. 70% of the lesson is about the covalent bonds and the covalent molecules. So we'll start with that. Right? Actually, with the first tute, we are to cover this. All the things you should know about the covalent bonds and the covalent molecules will be studied with the first tute. Right? So these things will be studied then with a different tute. Right? So that is just the outline of the lesson. So at the first page, you can go to the note and see. Let's quickly go to the note and see whether we had discussed all the things at the note, right? See, it is said, first point. Chemical bonds are and structure of molecules are conceptual models based on the modern atomic model in order to explain the physical and chemical properties of matter. Right? To explain the chemical and physical properties, we use these models, right? The bonds, right? We'll discuss those things. Many atoms do not have stable outermost valence shell configurations. Therefore, chemical bonds occur between atoms in order to achieve stability. Yeah, the main purpose of forming chemical bonds is actually to achieve the stability. So most of the atoms, are not with the stable configurations, right? Only the noble gases are with the stable configurations. So atoms try to achieve stability by coming up with stable configurations by fulfilling their octets, so they're fulfilling their valence shells, right? So that is why the atoms tends to form covalent bonds. We'll study those things, right, with those bonds, right? Third point, valence electrons participate in chemical bonding using three main conceptual models. Those are the three: covalent bonds, ionic bonds, and metallic bonds. Those will be referred to as primary bonds, right? Okay, that is there. So let's start with the covalent bond, right? Our major first discussion is going to be about the covalent bond, right? Okay, let's start. So today we are going to discuss about the covalent bond, and basically we are going to start drawing Lewis structures. That is our major focus today, right? Okay, let's start with the covalent bond. Right, our subtopic is covalent bond. Covalent bond and the covalent molecules. Right. So we know about the covalent bonds, right? So when it comes to covalent bonds, what are those? Basically, when atoms binds to each other with the use of shared pair of electrons, right? Then we call such a connection as a covalent bond. See, right? In small ages, you may have, right, drawn these things, right, with Lewis structures and stuff, right? When it comes to atoms, like, see, chlorine. Two chlorine guys are connected via covalent bonds. See, if you draw the chlorine molecule, Cl2, right? It will be like this, no? So 7 electrons are there at the valence shell of chlorine. So those will be marked like this with this chlorine. Another 7 electrons are there. So dot cross structures you may have drawn in your O levels, right? So this is referred to as the shared pair. This is referred to as shared pair. This is what we refer to as the covalent bond. The shared pair. The shared pair is referred to as a covalent bond. Right? That is what it says, right? So covalent bonds are the bonds which formed by shared pair of electrons. Normally, when forming a covalent bond, one electron comes from one atom and the other electron comes from another atom. Normally, that is how the two electrons are given to the bond, right? One electron from one atom and the other electron from other atom. So that is normal situation, right? See, another situation, another instance, right? When you are thinking of H2O molecule, right? This is your Lewis structure, no? The hydrogens and oxygens. Oxygen is with 6 electrons at its valence shell, 1, 2, 3, 4, 5 and 6. The hydrogen is with 1 electron, see? So Actually, these are covalent bonds, no? Here, as well as here, you see the formation of covalent bonds. Right, so sharing electron pair, sharing an electron pair between two atoms is referred to as a covalent bond, right? That is the idea. Normally one electron is given by one atom and the other is given by another atom. That is the normal way of forming a covalent bond, right? Okay, let's go to the note. It says covalent bonds are formed when a pair of electrons is shared between two atoms of, right, two atoms of same element or different elements, two atoms of same element or different elements between the oxygen and hydrogen. So that you can form covalent bonds like that, right? So next point, it says the sharing pair of electrons contribute one electron from each atom to form an electron pair. The sharing pair of electrons contribute one electron from each atom to form the electron pair. This electron is given by the hydrogen and this from the oxygen. So sharing pair is normally formed by one electron each given by each of the atoms, right? Okay, that is normal way of forming covalent bonds. But remember, in A levels we are going to study about another kind of covalent bonds, right? Where both the electrons are actually shared by one single atom. This is some kind of example. See, when you have NH3 molecule, like this, so let's consider NH3. So the NH3 is like this, no? So let's think of NH3. Right? This is the nitrogen, and these are the hydrogens. This is your NH3 molecule. Right? So if it is to bonded with BF3, kind of a BF3, NH3 with BF3, right? When that is to happen, you will see a new kind of bond forming. BF3 is this, right? So between these two molecules, you will see a new kind of bond forming between these two guys by sharing this pair on nitrogen between two atoms. First, what will happen is, first this electron will be moved to here like this. Then a bond will make between these two guys, right? Such kind of bonds are also available, right? First, actually with NH3, the electron was like this. This is NH3. Nitrogen should have 5 electrons around it, right? Nitrogen is as group 15 element, right? So 2, 5, no? 5 should be there. But we can think of a bond between the nitrogen and boron by sharing this one of these electrons to here, and then it can form a bond between these two, right? So both the sharing pair there is actually supplied by the same atom. Such kind of situation is referred to as a dative covalent bond. So I'll write that thing as well, right? So when these two are to react, you will form this kind of a molecule. Right? NH3, right? The crosses are nitrogen's electrons, right? With the BF3. So B, right? F3. BF3. Right, that is about the BF3. See, this pair is actually belongs to nitrogen. So one can write this as like this. Actually, both the pair belongs to nitrogen. First, that is given to the boron. One is given to the boron and then shared. So This is referred to as a dative covalent bond. Dative covalent bond. We'll discuss about these bonds later, not today, but at the midpoint of this discussion, right? Discussion of covalent bonds, right? We'll discuss about these dative covalent bonds where both the electron pair is shared by one single atom, right? That is actually written there, right? It is said in your note. Let's go to that. Sharing of an electron pair between two atoms in which both electrons are given by one atom is called dative covalent bond, right? It's a dative bond or dative covalent bond, right? That is the idea. Okay, so we have learned two types of covalent bonds: the normal covalent bonds where the two electrons are shared one each by two atoms, right? And then comes the dative covalent bonds where both the electrons are shared by one single atom, right? Okay, those are two types of covalent bonds possible, right? Anyway, to form a covalent bond, there should be an electron pair between two atoms, right? Okay, right. Are you clear, Chris? Do you have any problems up to the work discussed here? No, it's clear. Right. Okay, this is about the covalent bonds, and we learned these things in your O level as well. Right. Let's come up with the next stuff. Right. Next one. So when it comes to these structures, the Lewis structures, what you have drawn, right? You may have drawn those things, right? In your O levels, the Lewis dot cross structures. You had drawn those things, no? Chris, right? Lewis dot cross structures. You have came through those, no? Yes, no? Okay, right. So when it comes to the Lewis dot cross structures, right? There is a very important rule called as octet rule. Called as octet rule. Octet rule. We'll discuss about this thing. When it comes to Lewis structures, there's a very important rule referred to as the octet rule. Yes, octet. Octet means 8 electrons. Octet means 8 electrons. Octet means 8 electrons. 8 electrons. So 8 electron rule. 8 electron rule. Octet rule means something related to 8 electrons. Octet. Okay. Let's let's discuss about the octet rule. What this means actually, right? There were three scientists, right? Langmuir, Kozil, and Lewis. Those are three scientists: Langmuir, Kozil, and Lewis. Those predicted or put forward some idea, like they said that when forming a stable compound, right? Normally, this when forming a stable compound in simple molecules, right? Normally, the second row nonmetals achieve their octets. Second row nonmetals achieve their octets. That is what Langmuir, Kozil, and Lewis observed, right? That is ultimately referred to as the octet rule. Let's discuss a bit about that thing. Let's come up with some simple molecules. The NH3. NH3. When it comes to NH3, again think of its Lewis structure. NH3, right? When it comes to NH3, right? As nitrogen is with 5 electrons at its valence shell, the nitrogen is with kind of 2, 5. Hydrogen is only with 1. No? So the structure is like this: 3 hydrogens giving 1 electron each, and 3 nitrogens contribute 1 electron each to the bonds, and another 2 is remaining. This is the NH3 structure. Right? If you have to consider the NH3 structure in your molecule, the number of electrons around the nitrogen in your molecule, you will clearly see 8 electrons are going around nitrogen. 8 electrons are going around nitrogen. See, 1, 2, 3, 4, 5. 5 of its own electrons, and now these 3 dots, the electrons earlier belongs to hydrogen, is also now going around nitrogen. So altogether 8 electrons are there around nitrogen, right? 8 electrons around nitrogen. See, the octet is complete with nitrogen, which is a second row non-metal. So another structure is consider the H2O. H2O. Consider H2O. You will see the same. These two electrons are belongs to hydrogens. These are oxygen electrons. So when it comes to oxygen, it is group 16. So you need to have 6 electrons around oxygen, 6 of its own electrons. 1, 2, 3, 4, 5, 6. So if you are to think of the oxygen molecule and the number of electrons going around the oxygen after the molecule is made, you clearly see 1, 2, 3, 4, 5, 6 from its own electrons and 2 from hydrogens as well. So altogether 8 electrons are going around oxygen. 6 from 6 electrons are there with the oxygen and 2 came from hydrogen. So altogether 8 electrons are going around oxygen at the H2O molecules. 8 electrons around oxygen. See, this is what referred to as the octet rule. 8 electrons, 8 electrons, or one can say 4 electron pairs, 4 pairs, 8 electrons, or one can say 4 pairs, 4 pairs. See, 1, 2, 3, 4. 4 pairs are appearing around the second row nonmetals. Here, nitrogen, 1, 2, 3, 4. That is the octet rule. That is even valid for carbon as well. See, the carbon. Think of the CH4, some simple molecules. CH4, these structures of simple molecules. The octet rule, right? So carbon's electrons are marked in cross. Hydrogen's electrons are with dots. So here also you see carbon contribute 4 electrons to the bonds and 4 electrons are coming from hydrogens. Altogether 8 electrons are now going around the carbon's valence shell. Right, 8 electrons around carbon, around the second row nonmetal. So 4 pairs around the carbon. So that is octet rule, right? Octet rule is that when it comes to second row nonmetals, carbon, nitrogen, oxygen kind of guys, it is essential to fulfill the octet, or it is essential to come up with 4 electronic pairs around them in a stable molecule. That is what octet rule means. Right? That was first proposed by the Cosell, Langmuir, and Lewis. Right? So that is the idea. Very simple idea. You may have heard that thing in O levels as well. Did you learn this thing in O levels, Chris?
Yes, sir.
Yes. No. Yes. Sir. Then no worries. Right? So that is the octet rule. So this is very important when regarding the second row nonmetals. Right? This is very important when regarding the second row nonmetals. The octet rule is not a must for the third row guys or the first row elements. For hydrogen, you can't come up with the octet. For hydrogen, maximum of 2 electrons can be there, as it is with only the 1s subshell. Only the first energy level is there. So only 2 electrons can be there as maximum number of electrons for the hydrogen and helium. So you can't think of an octet there for the hydrogen and helium. When it comes to the third row above, sulfur, chlorine, right? Like phosphorus kind of things. No, it is not a must to fulfill the octet. Why is that? Because with the third row, SPD, all the subshells are available with the third row elements. So S can have 2 electrons as maximum, P can have 6, and D can have 10 electrons as maximum. So up to 18 electrons you can fill with the third row elements, with the third energy level. So that octet is not a must. You can exceed the octet with the third row elements. But when it comes to second row nonmetals, second row elements, right? It is a must if you are dealing with a even numbered electronic structure. If you are dealing with a even numbered electronic structure, octet is a must for second row nonmetals. When it comes to second row, only the S and P subshells are there. In S subshell, you can have maximum of 2 electrons. In P subshell, you can have maximum of 8 electrons. So altogether, it is going to be, sorry, S subshell you can have maximum of 2 electrons. P subshell you can have 6 electrons as maximum. So altogether it is going to be 8 electrons. So when your valence shell is the second row, the second shell, right, you should come up with octet if you are dealing with a even numbered molecule, right? So octet rule is a must for second row nonmetals, not for all the elements. Keep that in mind, right? So let's go to the note. It says, right, the octet rule. Kossel, Langmuir, and Lewis stated that the filling of electrons into a valence shell up to the maximum value of 8 results a stable electron configuration, hence called the octet rule. So the maximum of valence electrons in 2s and 2p orbitals of elements in second period is 8. So elements in second period, the C and OF, complete the octet when forming chemical bonds, thereby achieving a greater stability, right? That was the idea about the octet rule, right? We are going to reuse this octet rule, right, heavily when we are to draw the Lewis structures involved in the second row nonmetals, carbon, nitrogen, oxygen, and fluorine, right? Okay, so that is the idea. So at the next page, at the page number 2, they have mentioned, actually we have mentioned some instances where you won't find the octet complete in situation, right? That could be possible, right? So that could be possible. So if you are with odd number of electrons, in your molecule, right, you can't think of an octet. To come up with octet, the pairs should be there. Always the pairs should be there. Always the pairs should be there to come up with the octet, right? If you are with kind of odd number of electrons in your molecule, then you can't think of octet, right? Such situations are available, right? So if you think of the NO molecule, there you go find the octet. So at the next page, that is what they are referring to, the situations where you won't find the octet. So if you are thinking of N and O, right, oxygen will come up with like this, NO molecule, right? Oxygen will come up with this 6 electrons, and nitrogen will also come up with 5 electrons, 2 there, 3, 4, and 5 electrons. So you clearly see nitrogen is unable to complete the octet, right? Only 1, 2, 3 pairs and half a pair. That means only 7 electrons are going on nitrogen. So this is not fulfilling the octet. So when you are with odd number of electrons in a molecule, right, you can't fulfill the octet for each and every atom. So nitrogen is not with the octet. Nitrogen is not with the, you can say nitrogen is not with the octet, right? So such situations are also there, right? Right. So we have 3 occasions where you won't follow the octet rule. That should be also known, right? So one instance is that when you are with odd number of electrons with your valence shell. The second instance is actually, right, some molecules like AlCl3, BH3 kind of stuff are there where you are not with 4 electrons in your neutral atom. Where you are not with 4 electrons in your neutral atom, then you can't come up with octet. See? So the second instance, this was first instance where you violate the octet rule. The second instance, right, it's like this. So when it comes to molecules like AlCl3, the aluminium atom is only with 3 electrons. Atom is only with 3 electrons. The aluminium, you know, it is 2, 8, 3 at the valence shell, only 3 electrons are there. So it can have, as normal bonds, it can combine only into 3 atoms. Like this, the chlorines. So you clearly see, right, aluminium is not going to fulfill the octet, as only 3 bonds can be formed with the aluminium, right? Only 3 pairs are going around the aluminium, right? That means only 6 electrons. So you are not fulfilling the octet, right? So that kind of situation happens when you are with only 2 or 3 electrons in your valence shell. You are not with 4 electrons in your valence shell, right? That is what happens when you are with such electronic configuration, right? You are unable to form 4 bonds. You are unable to come up with 4 pairs. You are unable to come up with 4 pairs. as you are only with 3 electrons in your valence shell, right? So such situations are there, those mentioned in your note, AlCl3, BH3, BF3 kind of things, right? Octet violation could occur. Third instance where the octet can be violated, right? The third instance is actually when you are with a third row or above non-metal, when you are with a third row or above non-metal, right? So when it comes to sulfur kind of thing, right? If you think of sulfur, right? Sulfur can have more than, right, more than the octet. See, if you are to come up with SO2 molecule, SO2 molecule, right? So this is the oxygen's 6 electrons, right? This oxygen is also with 6 electrons. Sulfur is also carrying some 6 electrons. 1, 2, 3, 4, no, 5, 6. Right? So if it is so, you clearly see how many number of electrons are electron pairs are appearing around sulfur. 1, 2, 3, 4, 5. 5 electronic pairs are around sulfur. 5 electronic pairs around sulfur means 10 electrons are going around sulfur. 10 electrons around sulfur. 5 electronic pairs, no? 5 electronic pairs. 5 pairs. So that is violating the octet rule. That is violating the octet rule, right? Octet rule means only 4 electron pairs are possible. Only 4 electron pairs are possible around a considering atom. So when it comes to SO3, SO2, right? 5 electronic pairs are going around the sulfur. So this is also kind of a octet rule violation, right? So 3 instances are there where you violate the octet rule, right? These are the 3 instances, right? So you should have some idea about that thing as well. So keep it in mind, octet is not a must, right? The octet is not a must, right? You can have some exceeded octet situations, and you can have some octet deficient situations, and you can have this kind of odd number of electron counts where you are unable to come up with octets, right? For all the atoms, right? So right, considering that, right, but there is a situation where the octet is a must. Yes, we can have these situations where the octet is violated, but if you are to think of second row nonmetals, if you think of second row nonmetals, then octet is going to be a must if you are dealing with a even numbered electron count. If you are dealing with a even numbered electron count, right, you see, for second row nonmetals with even numbered electron count, octet is a must. Octet is a must, right? You can't have exceeded octet as well as you can't have deficient octets with second row nonmetals with even numbered electrons, right? With second row nonmetals with even numbered total electrons, right? Second row nonmetals with even number of total electrons, octet is a must. Octet is a must. See, right? 4 pairs are appearing, right? Second nonmetal means CNOs, carbon nitrogen oxygens, even the fluorine. Right now, this is all about the octet rule, right? Are you clear about the ideas discussed so far, Chris? Oh, Chris is gone, right? Okay, right. What happened to Chris, right? So just send a message to Chris. Okay, so that is about the octet rule. Okay, let's discuss about the Lewis structures now. So we have learned about the octet rule, right? So let's go to the discussion about the Lewis structures. That is the main focus today, right? Okay, now let's come up with the Lewis structures, right? So in A levels, right? We are going to draw, right, dot dash structures as Lewis structures, right? Dot dash structures, right? So in small ages in O levels, you have drawn the dot cross structures. Now in A levels, we are going to draw the dot dash structures, right? So here in A levels, we are going to draw the dot dash structures, not the dot cross, right? Let's discuss how to draw a dot dash structure. It's not hard now. It is not hard. So I'll give you some examples, right? So let's take the Cl2. In all levels, you have drawn the Cl2 like this. Two chlorines, right? As chlorine, when it comes to chlorine, no? When it comes to chlorine, right? The chlorine is with 287, no? At the valence shell, you have 7 neutrons, no? So you had drawn like this the 7 neutrons of your chlorine, one here, and for the other chlorine, another 7 neutrons, no? That is how you have drawn the Lewis dot cross structure of chlorine. No? This is the dot cross structure. Dot dash means this. It's very easy to draw the dot dash, right? What you are doing is you are not supposed to draw the circles. You're not supposed to draw the circles. Just put the two atoms and the sharing pairs, the sharing electron pairs are marked as dashes. The sharing electron pairs or the bonds are marked as dashes, and all the other electrons, all the other valence electrons are marked as dots. All the other valence electrons are marked as dots. We are not writing crosses, right? All the other valence electrons are marked as dots. Even the cross things are marked as dots. This is the dot dash structure. Right? In a Lewis dot dash structure, right, you will see the dots and dashes, right? Actually, dots represent, right, electron pairs which are actually non-bonded electron pairs. The dots represent the non-bonded electron pairs at the valence shell, right? Those are actually known as lone pairs. What are lone pairs? Those are the non-bonded electron pairs at valence shell. Non-bonded electron pairs at the valence shell are known as lone pairs. Actually, those are denoted in dots in your dot dash structure. And then there will be dashes, and the dashes are the bonded pairs. Bonded or bonding electron pairs, or bonded or bonding pairs. Those are the electron pairs in covalent bonds, right? That is how a dot dash structure is formed. Right? That is how a dot dash structure is formed. So you can mark these things in the note as well. The dots are the lone pairs, the non-bonded electron pairs at the valence shell, and dashes are the bonding pairs. So let's discuss about another one, another structure. So O2. So oxygen is with 2 and 6, no? 8th atom, no? So at a valence shell you have 6 electrons, no? So So let's come up with the O2 structure. In your small ages, you had drawn the O2 like this. So 6 electrons are there with the oxygens. Sorry. Right? Yeah, 6 electrons are there with the oxygen. 4, 5, 6. And with this one as well, 6 electrons are there. This is how the O2 is drawn as a dot cross structure. But now in A levels, we are present to those dash structures. How to draw? First, you are not drawing the circles now. Just 2 oxygens, and the bonded pairs are marked in dashes. So 2 bonded pairs. So 2 dashes should be there, and non-bonded pairs are marked in crosses. Right? You have 2 non-bonded pairs around one oxygen, and around the other oxygen as well, you have 2 non-bonded electronic pairs, the lone pairs. This is your dot dash structure of O2 molecule, right? So got the idea? That is how the structures are to be drawn. Let's come up with another one if you need. HCl. So normally you are drawing like this. H and Cl. So when it comes to Cl, right, you have this structure 287. So 7 electrons are there around the chlorine, right? So 1, 2, 3, 4, 5, 6, and 7. Around hydrogen, it's only 1 electron, right? So let's come up with the dot dash structure of the HCl. You're not drawing the circles, just the H and Cl, and you have only one bonded pair, that is a covalent bond, and you are with 1, 2, 3 shared electronic pairs. So those will be marked as dots. Sorry, 1, 2, 3 non-bonded pairs. Sorry, only one shared electron pair and 3 non-bonded pairs. Those will be marked as lone pairs. Right now, this is the Lewis structure, Lewis dot dash structure of HCl. Right now, that is the idea. Okay. Right. That is all about you should know about the dot dash structures. The simple idea. Right. After this, we'll try to draw some complex structures. Right. Here, actually, what we have drawn is just simple structures only with 2 atoms. Right? Only with 2 atoms. In A levels, we are supposed to draw Lewis structures with more than 2 atoms. 3, 4, 5, 6, 7 even. With a greater number of atoms, we should be able to draw the Lewis structure when they have asked, right? Okay, let's try to come up with those complex Lewis structures. I mean, complex compared to these, right? Okay, so let's come up with those structures, right? So anyway, we are going to draw only the dot dash structures in A levels, right? Let's come up with some bit complex ones than these, right? Let's discuss about the theories we need to follow to draw those, right? Okay. Right, drawing Lewis structures we'll discuss in 2 sections, with 2 sections, right? So first we'll discuss with simple molecules where you are with only one central atom, where you are with only 1 or 2 central atoms, right? So first we'll discuss about how to draw those structures, right? When you are with only 1 or 2 central atoms, right? After learning about those, we'll go for the complex situations where you find more than 2 central atoms in your Lewis structure, right? First, we'll start with the discussion, right, of Lewis structures with only 1 or 2 central atoms, right? Okay, so under that, right? We are first concerning about the Lewis structures with central atoms of second row nonmetals, right? First we will concern about the Lewis structures with central atoms of only the second row nonmetals, right? Okay, that is our first discussion today, right? So drawing Lewis structures, right? So we'll erase this thing as well, come up with the topic there, right? So it's about drawing Lewis structures for species with central atoms in second row. Normally those are the carbon, nitrogen and oxygen, right? Let's discuss about these Lewis structures, right? Where you find the second row nonmetals as your central atoms in Lewis structures, right? Here the very simple things are considered under this topic. Normally we are having up to 2 central atoms, right? Okay, if you are with more than 2 central atoms, some other, right, method is there to come up with the structure, correct structure in no time, right? But here we are referring to structures with central atoms only up to 2, right? Okay, and here we are discussing about the structures with second order nonmetals only, right? Okay, let's see how to draw this kind of a structure. So first with an example, let's discuss about the steps involving this section, right? So let's come up with the example. Let's try to draw the Lewis structure of NO2 minus ion. Lewis structure of NO2 minus ion, right? Okay, let's consider that. Okay, let's discuss about drawing the Lewis structure of NO2 minus ion. Let's discuss the steps of drawing NO2 minus ion Lewis structure, right? Okay, few steps are there. First one, the step 1. Step 1 is drawing the skeleton. Step 1 is drawing the skeleton of this thing. Drawing the skeleton means drawing the skeleton, right? Drawing the skeleton means you are supposed to come up with the correct atomic connectivity. Right? Skeleton means that how the atoms are connected to each other. So whether this is the skeleton or whether this is the skeleton. So NO2 minus this, you have 1 nitrogen atom and 2 oxygen atoms in your structure, right? So this is this is one possibility. This is the other possibility. So which is the correct skeleton? So doing the correct skeleton is what we are discussing now, right? So when drawing the correct skeleton, coming up with the correct skeleton, there are 2 major things to consider. Those are actually written in your book, right? Let's go to those. The 2 things are, first thing is actually the hydrogen and fluorine. Hydrogen and fluorine never comes as the central atom. So hydrogen and fluorine can form only one bond each. By forming the one bond, they will complete their valence shell so that no further bonds can be formed. So the hydrogen and fluorine never comes as a central atom. You can identify central atoms, no? Central atom means, so if you are thinking of atom, right? So skeleton, central atom means if the atom is connected to more than one atom, if the atom is connected to more than one atom, this is your central atom. Central atom. These are referred to as terminal atoms or the cone atoms. The atoms which connected to only one bond is referred to as terminal or cone atoms. Central atoms are the ones, they are, right, you are with more than one bonds, right? Okay, so hydrogen and fluorine never comes as central atoms, right? That is the first consideration when coming up with the correct skeleton. The second thing is, right, that is the most important point, right? When selecting the central atom, you should come up with the least iterative atom as the central atom. You should come up with the least iterative atom as the central atom. That is very clear, right? That is a very logical idea. See why it's so? So we know normally we know when going towards, right, when going towards right, atomic radius decreases, size decreases. Size is larger here, size is smaller here. When going towards right of a period, it is what happens. Size decreases. When going towards right of a period, eternity increases. Eternity increases. Right? Is the eternity, right? Eternity increases, you know, no? When going towards right, the eternity increases. Right? The least iterative atom means that is the atom with the larger size. So actually, if you are with large atoms, that can connect to more atoms. If you are larger, you can connect to more atoms than an atom with smaller size. Right? So more probability of forming bonds is there when your size is large than a small size atom. So that is why we say always come up with the least iterative or the electropositive atom as a central atom. So for a central atom to be, right, it should be able to come up with greater number of bonds, right? That is what the idea is, right? So it is better to come up with the least iterative atom as a central atom. So when we consider in the eternities of these guys, right, the nitrogen's eternity is what? Nitrogen's eternity is 3.0 and the oxygen's eternity is 3.5. So we have to take the 3.0, the least iterative atom, as a central atom, so that this is not going to be structure, this is the structure, nitrogen at the center. So that is how we are supposed to come up with the correct skeleton, right now. So your correct skeleton for NO2 minus is this, right? Least iterative atom at the center, as a center atom, right now. That is the first step, right? We have to follow when coming up with the collective structure. First step, right? Just draw the least iterative atom at the center and complete the skeleton, right? It is done, right? Let's come up with the second step then, right? Second step. Now we are going towards second step. Step number 2. Right? Step number 2. So I'll put it here, no? Same thing. Step number 2. Step number 2 is coming up with the valence electron count. Valence electron count. This is also known as VEC, valence electron count. Let's do that. Valence electron count. Valence electron count means, right, that is all about the how the valence electrons, the financial electrons, are contributed among the atoms. It is what referred to as the valence electron count. See, so nitrogen, as it's a group 15 element, its valence shell is with 5 electrons, right? 2 oxygens are there. That means oxygen is group 16 element, so 1 oxygen gives 6 electrons to the valence electron count. Group 16 element means 6 electrons are at the valence shell. Such 2 oxygen atoms are there. So together 12 electrons are contributing towards the valence electron count from oxygens, 2 oxygens. And then this -1 charge. -1 charge means you are now with excess of 1 electron. That 1 electron is added than the electrons with the nitrogen and 2 oxygens. Than the electrons with nitrogen and 2 oxygens, 1 more electron is added. That is why the minus charge is there. When you are adding electrons, the anions are formed by adding electrons. Anions are formed by adding electrons. So NO2 minus means you have added 1 more electron. -1, 1 more electron to NO2, right? So that should be marked as well. So with anions and cations, always the valence electrons are involved, right? So 1 more electron is added to the valence shell, right? So the valence electron count, the total number of valence electrons are going to be 18 electrons. 18 electrons. So with the valence electron count, we are expected to come up with how these 18 electrons are distributed, right? So 18 electrons are there. So electron pairs, 18 electrons means number of electron pairs is equal to 9 pairs. 9 pairs. So we are always referring to pairs, right? 9 pairs. Right. Then for your skeleton, already 2 pairs are used. 2 pairs are used for the skeleton. For the skeleton, right? 2 pairs are used. So we have to deduct those 2 pairs. So you will come up with 7 pairs as remaining. Those are actually considered as lone pairs. Those are considered as lone pairs. So 7 lone pairs are there in your NO2 minus molecule. That is what the VEC says. That is the end of the second step. Right? Drawing Lewis structure. This is the second step. Counting the valence electron count. Right now? So 7 electronic pairs. Right now? Okay, let's go to the third step. Third step. Okay. Step number 3. Step number 3. Right? Step number 3 is allocating those 7 pairs or giving those 7 pairs to the skeleton. Right? Okay? So that is the third step. Right? Giving the or allocating the lone pairs to skeleton. Right? 7 pairs are there. So let's come up with 7 pairs. We have to provide those to the skeleton. Right? So when allocating those pairs, 7 pairs to these atoms in your skeleton, right? You can't allocate all the 7 pairs to one atom. You can't allocate all the 7 pairs to one atom. Right? So to which extent we can go for? That is the major question arise now. Right? How many electronic pairs should be given to this oxygen? How many electronic pairs should be given to the nitrogen and to the other oxygen. Whether we are supposed to divide the 7 into three sections and provide that thing, is that the case? Is that the way of providing the electrons to electron pairs to the atoms, or any other way? Or which atom, to which atom we should supply the electrons first, the electron pairs first, to the nitrogen or oxygen? Those are some questions arising when you are thinking of providing these 7 pairs to these atoms in your skeleton, right? Okay, the points are these. The major concerns are these. First thing, right? The idea is this. The first allocation of electronic pairs, or first allocation of electronic pairs, should be given actually to the most electronegative atoms in your system. To the most electronegative atoms of your system. Because the most electronegative atoms are the most keen guys of electrons. So that first you should provide the electrons to oxygens, these 2 oxygens. If still the electrons are remaining, electron pairs are remaining, then only you can provide that into nitrogen. That is the idea. So simply we can say, first allocate the lone pairs, or first give the lone pairs to the corner atoms, Then if the still pairs are remaining, then you can provide them to the center atom. That is the first rule. First give the electrons to the corner atoms, right? If still remaining, then you can give to the center atom. That is first point to keep in mind. Second point, how many electrons are supposed to give to the oxygens? How many electrons are supposed to give to the oxygens? That is the next question arise. So you can't give all the 7 pairs to this oxygen, right? Okay. What is the major concern? The octet rule, right? The octet rule. So basically, what we are doing here is, as we are looking for a stable molecule, what we are doing is actually we fulfill the octets of the corner atoms first. We fulfill the octet of the 4 atoms first. Octet means the 4 pairs. We give 4 pairs to the 4 atoms first, and then if the electrons are still remaining, then we give them to the center atom. That is the idea, right? Okay, let's provide them. So already this oxygen is with 1 pair. Already this oxygen is with 1 pair. So giving the octet means completing the 4 pair situation. So 1 is there, 2, 3, 4. Now 4 pairs are there around the oxygen. Octet is completed, right? Then for this oxygen, 1 pair is there as a bonded pair, 2, 3, 4. 4 pairs are given to corner atoms. That is the first thing what we should do, providing the octet for the corner atoms. Then if still electron pairs are remaining, then give that to the center atom. That is the way of allocating electronic pairs to the skeleton, right? Okay, so already 1, 2, 3, 4, 5, 6 have been given. So this should be the 7th one, right? Is still remaining. Just give it to the center atom, right? Now that is the step number 3, right? Step number 3, giving the lone pairs to the skeleton, right? What was the major focus there? That was first you should fulfill the octet of the corner atoms. If still remaining, then you can provide that to the center atom. That is how we are supposed to complete the. That is how we are supposed to allocate the lone pairs to the skeleton, right now. Right. Let's discuss about the 4th step of drawing a Lewis structure. 4th step. Step number 4. Step number 4. Step number 4. The 4th step says, this is very important, right? As we are dealing with second row nonmetals, basically that is our topic, right? They are second row nonmetals as central atoms, right? Providing the octet for them is a must. Providing the octet for them is a must if you are dealing with even numbered electron count. Even numbered electron count. if you're dealing with even numbered electron count, providing the octet for the second order nonmetals is a must. But now this guy is not with the octet. Only 1, 2, 3, 1, 2, 3, 3 pairs are going on the nitrogen. That means only 6 electrons are going on nitrogen. So we have problem there. We have problem there. So the fourth step is to complete the octet of the second row nonmetal, which means the central atom. So completing the octet of central atom. As a central atom is kind of a second order nonmetal, right? We have to complete the octet for those. Because these are completed, right? For the cone atoms, we have completed at the third step, right? So we have problem with the center atom now. It is not fulfilled. The octet is not fulfilled. Okay, so now we are up to the fourth step. So we have to complete the 4-pair situation with this nitrogen. We have to complete the 4-pair situation with this nitrogen. So we can do like this. So we can provide one electronic pair from here. One electronic pair from here. So if you have to provide one electron pair from here, right? Your structure, right, will look like. Right, I'll draw it here. Your structure will look like this. Right now, this will be your structure. So one electron pair is given to here, so bond will be formed. So this is your structure looks like now. So now you clearly see this guy fulfilled the octet. 1, 2, 3, 4. 1, 2, 3, 4. 4 electron pairs are going on nitrogen. That means the octet is there. 4 pairs means 8 electrons. So you see now the octet is fulfilled with all the 3 atoms, all the second order nonmetals. So providing electron pair like this won't affect the octet situation of the cone atoms. Right, giving some electron pair towards the center atom like this won't affect the octet of the central of the cone atom. You see, still 1, 2, 3, 4. Still 4 pairs are appearing around the cone atoms, right? 1, 2, 3, 4. No worries. So octets are there, right? That is how we are supposed to fulfill the octets of these things. So one can come up with like this as well, right? If this is not the case, one can supply this pair towards that, right? So that you will come up with a structure like this. This is also acceptable, right? No worries. That can be also done. This is also acceptable, right? 2 possible ways of providing the octet towards the second order nonmetal, the center atom, right now. So that is the fourth step. This is the fourth step. I'll draw this in red color, right? Because that is because the red color movement, electronic arrangement, right? Right now, these are 2 possible ways. Anyway, drawing 1 is enough, right? Drawing 1 is enough. No need to draw this ways, right? And just completing 1 thing is enough, right? Okay, that was the fourth step. Now we are leading up to the final step of drawing or completing the structure, right? The final step, step number 5. Let's complete step number 5. Step number 5. It is said as assigning formal charges. Assigning formal charges to atoms. Okay. What this means? Formal charge. What this means? Actually, formal charge means the charge on your atom. The charge on your atom is referred to as the formal charge of the atom, right? So this is the charge of the ion. This is charge of the ion. So formal charge is the charge on each and every atom. Charges on atoms are referred to as the formal charges. This is the charge of the whole species, NO2 minus ion. Now we are referring to charges on atoms. So our two structures are like this now. These are two resultant structures after the fourth step. Now we are supposed to assign formal charges to these structures. Right? Assigning formal charges. Okay, how to do? So there is a formula. There is a formula to come up with the formal charge. This is about the formula, right? Formal charge, right? The formal charge, let's say it has Fc. Formal charge is given by actually the number of electrons there should be with your atom. The number of electrons there should be with your atom. Number of electrons there should be at the valence shell. That means the group number. That means the group number. So when it comes to an atom, number of electrons there should be around the atom is the group number. With nitrogen at the valence shell you should have 5 electrons. With oxygen at the valence shell you should have 6 electrons. Those are the number of electrons there should be at the valence shell. That means actually the group number. Group 15 with 5 electrons, right? Group number, the 5A number, the A number. The A number, right? 5A, no? 5 with nitrogen, right? 6 with oxygen. Minus number of electrons assigned so far. That is how we are supposed to come up with the formal charge. Group number minus number of electrons assigned so far. Just use this formula to come up with the formal charge of these guys, right? Let's come up with the formal charge of this oxygen. For the oxygen, right? The group number is group 16 or 6A. Group number is 6. 6A minus number of electrons assigned so far. Let's count number of electrons assigned so far. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Only the oxygen's electrons are counted. Only the oxygen's electrons are to be counted, right? 1, 2, 3, 4. So number of electrons assigned so far 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 minus 6 is going to be 0. The formal charge on this oxygen is 0. What about this? Let's calculate the formal charge of nitrogen. So number of electrons there should be with the atom at the valence shell, the group number. The 5A, group 5A, nitrogen minus 2. That means 5 electrons should be there with nitrogen. Now, how many electrons are assigned? 1, 2, 3, 4, 5. Only the nitrogen electrons are counted, right? 1, 2, 3, 4, 5. 5 should be there. Now you have 5. The formal charge is going to be 0 then. What about this oxygen? Formal charge of that oxygen, right? Count. First of all, how many electrons there should be? As it's a group 16 or 6A element, there should be 6 electrons at the valence shell. Minus number of electrons assigned so far is actually 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. So that oxygen carries kind of minus 1 charge. Minus 1 charge, so that we have to assign that thing, minus 1 charge, minus 1 charge. So we have to assign the charge with that atom, minus 1. No need to put 1 there, just minus 1. If you are with greater than 1 unit of magnitude, then you can put the 2, 3 like that. Minus 2 can be written as minus 2, minus 3 can be written as minus 3, but for the minus 1, just writing minus is enough, right? So that is the Lewis structure. That is the Lewis structure of NO2 minus. If you are to assign charges of these things, this will carry with carry zero charge, this will carry zero charge, and this will come up with a minus charge. You can do the same calculation with this one as well. So these are two acceptable Lewis structures for NO2 minus. Right? This is how a Lewis structure is drawn. Right now, these are the answers. So if you had written or drawn this structure correctly, the summation of former charges should be equal to the charge indicated at the upper right corner of the chemical species. So summation is 0, 0, minus 1 is minus 1. That should be the charge indicated at the upper right corner of the chemical species. Here also minus 1, 0, 0. The summation is minus 1. That is here. Right? That is how you are supposed to come up with a Lewis structure with second row nonmetal at the center atom. Right now? Okay? Clear? That is the idea. So we'll draw some few more Lewis structures. So this is about the NO2 minus. Both are acceptable Lewis structures. Right now? Let's come up with few more. Right? So you have much work to do in your book, right? So some other structures are to be drawn. Just start drawing them. We'll discuss those things. Right? The CO2. What are the structures given there? Right? What are the structures there? See. In your next page, page number 5. Right? At the bottom of page number 4, no? Some questions are there. Draw some Lewis structures for the species given below. Let's try to draw those. Let's start with CO2. Let's do. Right? Okay. First, copy this one. Right? And then start drawing the Lewis structures at the bottom of the page number 4. Right? Okay, let's try to draw a few more structures. Right. I'll draw a few more structures, right? So these are the structures appearing with your questions, right? CO2, the NO2 plus. Third one is NO3 minus. Fourth, HCN. Fifth is carbon monoxide. Right? First we'll draw these things. First I draw these structures, right? Okay, let's start with CO2. First thing to come up with is with the skeleton, right? How to draw the skeleton? So least unitary atom should be taken as the central atom. So the unity of this thing is carbon is 2.5, oxygen is 3.0. So least unitary atom should be taken as the central atom. So the carbon should be at the center. This is skeleton. First step done. Second step, coming up with the valence electron count. Valence electron count, right? Carbon, as it's a group 14 element, 4 electrons are at the valence shell. Oxygen, as it's a group 16 element, right? 6 electrons are at the valence shell. Such 2 oxygens are there. You don't have a charge, that means you don't have excess of electrons, so you are not with lack of electrons. So the electron count says is 16 electrons. Electron pairs, (16O2) means 8 pairs. 8 pairs. So for the skeleton already, right, 2 are assigned. So 2 electron pairs should be deducted as they have used for the skeleton. So number of remaining electron pairs are 6 pairs. Those are the lone pairs which we are supposed to assign to the skeleton. Right now, the second step done. Coming up with the VEC, valence electron count. Let's come with the third step. Third step means you have to assign these 6 pairs to the skeleton. They are, first we try to complete the octet of the cone atoms. If still remaining, then we will give those to the center atom. Completing the octet of the cone atom means, right, completing the 4 pair situations with the cone atoms. Okay, let's complete that. So 1 electron pair is there. So to complete the octet or to provide the 4 pairs, the 3 pairs should be given for this oxygen as well. So after completing the octet, the 4 pair situations with the 2 oxygens, all our 6 electrons are gone, right? This is the third step. Okay, the fourth step, next step is actually, right, to complete the octet of the central atom. If it is a second order nonmetal at the center, you need to complete the octet of that thing. You need to provide the 4 pair situation for that central atom if it is a second order nonmetal. So let's try to come up with that. So basically, to complete the octet, another 2 pairs, and the 2 electronic pairs should be given to the carbon. So we can allocate those pairs from here, one from here, and one from here. Right? So with that, you will come up with this kind of structure. Right? 2 pairs each with 2 oxygens as bonded pairs. These are the remaining lone pairs after you had allocated the pairs towards the carbon. So as these 2 pairs are given to this place, right, further longer, those are not appearing with this oxygen, this oxygen as well, as those are given to the space in between. So this is the electron arrangement, right? This is the electron arrangement with the CO2, as we are to fulfill the octets of the all the atoms. Right now, the final step is providing the formal charges, if any, assigning the formal charges, if any. So let's come up with the formal charges of these atoms, right? Oxygen, it is a group 16 element, 6 electrons should be there with the oxygen. Now we have allocated 1, 2, 3, 4, 5, 6. 6 should be there, 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So no charge with the oxygen. With the carbon, carbon is group 14 element or 4A element. Group 4A means there should be 4 electrons around carbon. You have allocated 1, 2, 3, 4. 4 should be there. You have allocated 4. 4 minus 4 is 0. No charge there. With this oxygen, oxygen should have 6 electrons around that thing. The group number, right? But now you have allocated 1, 2, 3, 4, 5, 6. 6 should be there and you have 6. So charge is 0. Right? So this is the structure of CO2. This is the correct structure of CO2. Right now? Okay, let's discuss about few more structures. Right. Next, let's come up with the NO2 plus. NO2 plus. Lewis structure of NO2 plus. Right. So first the skeleton. So nitrogen certainty is 3.0. Oxygen certainty is 3.5. So the least certainty one should be selected as the center atom. So nitrogen should be the center atom, right? So for the skeleton, it should be a skeleton with nitrogen at the center. Right now? Then we are supposed to come up with the valence electron count for the NO2 plus. See, nitrogen as group 15 or 5A element, it gives 5 electrons to the valence electron count. Oxygens are with 6 electrons at the valence shell. So 2 oxygens are there. So 6 into 2 plus, right? So NO2 plus, right? NO2 plus. NO2 plus means you had formed a cation. Cation means plus one. Cation means you had removed one electron. You had removed one electron from NO2. That means removed one electron. So from your valence electron count, one is removed. Right? So that altogether it is going to be, right, 16 electrons. 16 electrons as the total number of valence electrons. Right? So then we need electron pairs. That means 16 over 2, 8 pairs. Then for the skeleton, 2 is used, 2 pairs used. So finally you will come up with 6 electron pairs. So we have 6 electron pairs to allocate to the skeleton. Right? So let's allocate those 6 pairs to the skeleton now. So first we are supposed to fulfill the octets of the cone atoms, fulfilling the 4 electronic pair situation for the cone atoms. So as those were with one bonding pair, right? 1, 2, 3, 4. 4 pairs are completed now, right? So 1, 2, 3, 4. 4 pairs are completed, means octets are completed. So all the 6 have been used now, right? That is the end of the third step, allocation of the electron pairs to the skeleton. Next step. The next step is you have to complete the octet of the central atom. If it is a second or non-metal, you have to complete the octet of second central atom if it is a second or non-metal, right? So only 2 pairs are going around the nitrogen. So another 2 pairs are required to complete the octet, 4 pairs situation, right? The octet. So you can provide 2 electron pairs from here and here. So that will give you this kind of electronic structure. Right? So electronic structure is done. All the guys are with 4 electronic pairs. That means all the guys are with octets. That is done. The final step. Don't forget the final step. The final step is assigning the formal charges. Assigning the formal charges for these atoms. Right? So let's assign them one by one. For the oxygens, there should be 6 electrons as well as electrons. Now you have 1, 2, 3, 4, 5, 6. You have assigned 1, 2, 3, 4, 5, 6. Only the oxygen's electrons are counted, right? So 6 should be there, and you have 6, so the charge is 0. With this nitrogen, there should be 5 electrons as well as electrons at the group, as the group number is 5, 5A. So, but now you have allocated only 1, 2, 3, 4. 5 should be there, 4 are there. That means 5 minus 4. 5 should be there, only allocated 4. Assigned so far is 4. So 5 minus 4, that is plus 1. This is plus 1. So the charge here is plus 1 for this nitrogen. Let's assign the charges for these ones, right? This oxygen. So 6 should be there, as oxygen is group 16. But now you have assigned 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 should be there. And you have assigned 6. That means 6 minus 6 is 0. So this is your correct structure, Lewis structure for the NO2 plus. So after allocating charges, formal charges, just see whether the summation of formal charges is equal to the charge indicated at the upper right corner of the species. Yes, 0, plus 1 and 0, that is equal to plus 1. The structure is acceptable. Right now? Okay, that is another actual Lewis structure for the NO2 plus. Right, let's come up with the other guys. NO3 minus. Right, NO3 minus. So we have done these two. Now we have the NO3 minus. Right, first select the central atom to come up with the skeleton. Nitrogen is with 3.0 and oxygen is 3.5. The least C20 atom should be concerned as the central atom. So it is the nitrogen. So the NO2 minus, NO3 minus is with this kind of a skeleton. Nitrogen at the center and the other 3 oxygens are connected to the nitrogen. Right? Okay. So the valence electron count. NO3 minus, right? Nitrogen providing 5 electrons to the valence electron count, as nitrogen is with 5 electrons at the valence shell. 3 oxygens, 1 oxygen contributes 6 electrons to the valence electron count, as those are with 6 electrons each with 3 oxygens, right? So such 3 oxygens are there, right? And you are with anion. Anion means you are added some electrons to the NO2, NO3, right? So 1 electron is added, minus 1, no? So plus 1. 1 electron is added. So number of electrons, total number of electrons at the valence electron count is actually 1824 electrons. So the pairs equal to 12 pairs. For the skeleton, now you have use 2 pairs. So total number of electron pairs remaining. Sorry, we had to use 3 pairs. Sorry for that. We had to use 3 pairs for the skeleton, right? So total number of electron pairs remaining is 9 pairs. Okay. Next step is to allocate these 9 pairs to your skeleton. So first task is to complete the octet of the cone atoms. Complete the octet of the cone atoms. Right? Completing the octet means giving them 4 pair situation, right? So already they are with 1 electronic pair. 2, 3, 4. 1 is there. 2, 3, 4. Completing the octet means there should be 4 pairs around those atoms. 4 pairs, 8 electrons now. 1 is there, 2, 3, 4. While completing the octets of the cone atoms, all our 9 electronic pairs have been used, right? So allocation of electronic pairs to the skeleton is done now, right? So next thing is to complete the octet of the central atom as you are with the second or non-metal as a central atom, right? So what we need to do? So we need to provide some 1 pair towards this nitrogen as it is lack of the octet. Only 3 pairs are going on the nitrogen, only 6 electrons. That means you need another pair going on nitrogen to complete this octet. So you can provide that pair from one of these oxygens, from here, here or here, from any one of these oxygens, right? You can provide that pair. So that will give you this kind of structure. Right. So after the electron movement, you will come up with this kind of electronic arrangement, right? Then the final step. What is the final step? The final step is actually, right, assigning the formal charges. Assigning the formal charges, right? Okay, let's assign. So oxygen should have 6 electrons, as it's a group 16, right? Now you have 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Nitrogen should have 5 electrons. Now you are with only 1, 2, 3, 4. 1, 2, 3, 4. 5 should be there. You are with only 4. That means it is plus 1. Plus 1. 5 should be there. You are with now only 1, 2, 3, 4. 4 of its own electrons. That means plus 1 charge should be there with the nitrogen. Right now? These oxygens. There should be 6 electrons around the oxygen, right? As it's group 16, right? Group number 6. The electrons now you are allocated to the oxygen. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Only the oxygen electrons are counted, right? So 6 minus 7 is minus 1. So minus 1 is a charge for that oxygen. The same thing appears with this oxygen as well, the minus 1. Right? So this is your structure for the NO3 minus. So ultimately just check whether the summation of charges will be equal to the charge indicated at the upper right corner of the chemical species. 0 plus 1 minus 1 is 0, right? And minus 1. So altogether it will give you minus 1 charge, that is here. So the structure is correct, right? No? That is the NO3 minus molecule. Let's come up with the HCN. Let's come up with the HCN structure. Right, you have to select the center atom first of all to come up with the skeleton. So hydrogen is at 2.1, carbon is at 2.4, and nitrogen is at 3.0. So looks like the hydrogen is your center atom. No, you never select the hydrogen as a center atom. You never select the hydrogen as a center atom, right? So that won't be the center atom then. At hydrogen and fluorine, never select as a center atom. We started with that, right? Why is that? Because hydrogen and fluorine can't form multiple bonds. Hydrogen and fluorine can't form multiple bonds. So, right, you can't select the hydrogen as the center atom, right? So, the center atom should be what then? It should be the carbon. The center atom should be carbon here, right? Let's draw the Lewis structure using carbon. Let's do the skeleton using carbon at the center, right? Okay. So your skeleton should be like this, then should be like this. Carbon at the center, the other atoms are connected to the carbon. So HCN should be come up with this kind of a skeleton, right? So the skeleton is that. So keep it in mind. Never select the hydrogen or the fluorine as a center atom. Those can't be, right? Because those can't form multiple bonds. They can form only one bond, right? So hydrogen and fluorine never comes as central atoms. So other than that, the constraint should be considered. So the least electron atom other than the carbon fluorine is going to be hydrogen and fluorine. It should be carbon. So carbon should be at the center atom, right? Okay. So skeleton is done. Now the valence electron count. HCN. So hydrogen giving you 1 electron as it's a group 1 element, right? So only 1 electron is appearing with the hydrogen, right? So with carbon, as it's a group 4 element, it will provide 4 electrons to the electron count. And nitrogen, as it's group 5 element, it will provide 5 electrons to the valence electron count. So total electron count. So it is altogether 10 electrons there. So electron pairs, right, are going to be 5 pairs, right? What about the skeleton? So your skeleton contains 2 bonds. So you have to deduct those 2 pairs there. So ultimately you will come up with 3 pairs. 3 pairs, right? So we have to allocate those 3 pairs to the skeleton. We have to allocate those 3 pairs to the skeleton, right? Okay. So what we need to do? So first, the octets of the corner atoms should be completed, right? First, the octet of the corner atoms should be completed. So the 2 corner atoms are the hydrogen and nitrogen, hydrogen and nitrogen. So we no need to complete the octet of the hydrogen because hydrogen can't have octet, right? So let's try to complete the octet of this one first, right? So 3 pairs are there. That means you can complete the octet of nitrogen like this because 4 pair situation can be provided for the nitrogen. So all the 3 pairs are now provided, assigned. So the allocation of electron pairs are done now. Right, allocation of the electron pairs are done now, right? So the next step, right? When it comes to next step, right? What we are supposed to do? So we are supposed to come up with the octet with the center atom, right? If it is a second row nonmetals, yes. Now the carbon is kind of a second row nonmetal, right? So we need to provide the octet, means the 4 pair situation to this carbon, right? So only 2 electronic pairs are going around the carbon. That means another 2 pairs should be provided to the carbon, right? Another 2 pairs should be provided to the carbon. So we can provide 2 pairs from nitrogen here, right? That will come up with this kind of electronic structure. 3 bonds between the carbon and nitrogen, as these 2 pairs came as bonded pairs, and that lone pair still appears at here. These are not appears with the structure because those are assigned to form bonds. So this is the electronic arrangement of HCN, right? After that, we are supposed to copy the charges, if any, right? So hydrogen should have 1 electron at the valence shell. Now it is only with 1 electron, so 1 minus 1 is 0, no charge there. Carbon should have 4 electrons as it's a group 14 or 4 element, right? Now it has 1, 2, 3, 4, 4 of its own electrons, so 4 minus 4 is 0, no charge there. The nitrogen should have 5 electrons at its valence shell, this number, right? Okay, so now you have 1, 2, 3, 4, 5. 5 should be there, and 5 is there. 5 minus 5 is 0, no charge there, right? So this is the correct Lewis structure for HCl. Right now, okay, it is about HCl, right? Okay, let's consider the Lewis structure of carbon monoxide, right? Carbon monoxide. The structure of carbon monoxide. Right? So first the skeleton. Actually, if you are with a two atom situation, if you are with a skeleton with two atoms, no need to concern about the central atom, right? There is no central atom there, right? Only two atoms are there. At least there should be three atoms to concern about a central atom. So two atoms are connected. This carbon is connected only to oxygen. Oxygen is connected only to carbon. So those are cone atoms. No worries there, right? So this is the skeleton. Then let's come up with the valence electron count for the carbon monoxide. Carbon is providing 4 electrons to the valence electron count because carbon is group 14 element, right? Then oxygen is there. Oxygen is group 16 element, so provide 6 electrons to the electron count, right? So it is going to be 10 electrons as valence electrons. So electron pairs then 10 over 2, 5 pairs. Then for the skeleton, right, one pair is used for this atomic connectivity, right? One pair is used. So you are remaining with 4 pairs. Right now, carbon monoxide. Right. So we are supposed to assign these 4 pairs to these guys. So both are cone atoms, right? No central atom there. So to each atom, we should supply the electron pairs first. Yes, it should be towards the most electronegative atom. Most electronegative atom. Which is the most electronegative atom? So oxygen is with 3.5 electronegativity. Carbon is with 2.5 electronegativity. So most electronegative atom is oxygen. So towards that, we need to supply the electrons first, right? Towards oxygen, we need to supply the electrons first. So fulfill the octet for that. So one pair is there. So fulfilling the octet means providing the 4 pair situation. So 2, 3, 4. 4 pairs are completed with the oxygen. Then if remaining, give to the other atom. Right? Okay. So that is how we are supposed to allocate the electronic pairs to the carbon monoxide. Right. Next step. Next step is seeing whether the octets are fulfilled with the second row nonmetals. We don't have a central atom here anyway. So we clearly see this carbon is not fulfilled, the octet. 4 pair situation is not there with the carbon. So we have problem. Only 2 pairs are around the carbon, 1 and 2. So we need 4 pairs. So that what we need to do, we have to provide 2 from here to here. So that is how the electronic arrangement should be when fulfilling the octets for the second row nonmetals. Right now, that is the carbon monoxide, right? So let's assign the charges as the final step. Assigning charges. So carbon should have 4 electrons. Carbon should have 4 electrons as it's group 14 or 4a. Now we have assigned 1, 2, 3, 4, 5. We have assigned 5 electrons. We have assigned 5 electrons. So the charge is -1. minus 1 with the carbon, right? Charge is minus 1. What about the oxygen? Oxygen should have 6 electrons, as it's a group 16 element. 6 should be there, 6A or 16 element. Now we have assigned 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 6 minus 5 is plus 1. So oxygen here carrying a plus 1 charge. This is the carbon monoxide structure. If you had drawn this properly, the summation of charges should be equal to the charge indicated at the upper right corner of the chemical species. Plus 1 minus 1 equals 0. The structure is done. Right now? That is the structure of the carbon monoxide. Okay? This is how we are supposed to draw the Lewis structures, right? So we had I have drawn 5 Lewis structures, right, with you. So another 5 are there in your tute. Another 5 are there, right? So just do them as your homework. As your homework, just do the other 5 Lewis structures appearing, right? Okay. Complete that, right? And complete this one, right? After that, we are heading up to the next part of the Lewis structures, where we are supposed to draw Lewis structures with central atoms, not with the second order non-modules, but with atoms with third row or above, right? That is our next discussion. So quickly complete this stuff, and then we'll go towards that right now. Okay, Lamai, let's discuss about the Lewis structures when you are with central atoms in third row or above, right? That is our next discussion, right? Okay, let's go to that. So our next discussion is on drawing Lewis structures for species with central atoms, right? In n equals 3 or greater than that, those rows. Right, like when you have considering the phosphorus, sulfur, chlorine, xenon, those kind of things, right? This is just how to draw an Lewis structure when you are with the third row above central atom, right? That is our discussion now, right? Okay, drawing Lewis structure of a structure, right, with a central atom with third row above, right? Okay, let's try. So I'll take as an example, I'll take the SO4 2 minus. I'll take the SO4 2 minus to give you kind of idea here, right? Okay. One thing you should clearly identify here is when you are dealing with third row or above, octet is not a must. Octet is not a must for your central atom now. As we are dealing with central atoms in third row or above, so octet is not a must. So you can have exceeded octet. You can have exceeded octet. Exceeded octets. So it's not a must. So that in these cases, our main focus is to, minimize the charges on atoms. That is our major focus here. Minimize the charges on atoms. Right? In this case, that is a major focus. Right? because octet is not a must, right? So we are mainly concerning on minimizing the charges on atom, right? So smaller charge on your atom, you are less reactive, right? That is the idea, no? So we are always trying to come up with a stable structure. So when it comes to say stable structure, these charges on atoms will be good, right? Greater the charges on your atoms, or you are with greater charge density, some huge charge on your atom will lead you to more reactivity, because opposite charges will attract heavily towards those greater charges, so that more reactive nature arise with such structures. So we are always trying to come up with minimum charges situation, right? So in this case, right, octet is not going to be a must, as you can have exceeded octets, right? So major focus is to, right, minimize the charges on atoms here, right? Keep it that in mind. Let's see, with that knowledge, let's see how to come up with a stable structure for these situations, right? Okay, right. So let's try for the SO42 minus, right? So first thing is actually coming up with the skeleton, right? Coming up with the skeleton. For that, always we should need to come up with the least heterogeneous atom as the skeleton at the center, right? So sulfur is with 2.5 eternity and oxygen is with 3.5 eternity. So the one with least eternity should come up as the center atom, right? So sulfur at the center. Okay, this is skeleton. This is skeleton, right? So then let's come up with the valence electron count. Right, valence electron count. So SO42 minus. So sulfur is group 16 element. So it is with 6 electrons at its valence shell. Oxygen is kind of a group 16 element again, 6A. So again 6 electrons are at the valence shell of those oxygens. So you have such 4 oxygens. So 2 minus means it's kind of an anion, right? So you have excess of 2 electrons than the electrons in the SO4, right? So that 2 should be added. So altogether it is going to be 32 electrons as total number of electrons at the valence shells of these atoms, right? So electron pairs, (32/2) will give you 16 pairs. So for the skeleton, right, they have used 1, 2, 3, 4. 1, 2, 3, 4. 4 pairs have been used. So the number of electrons we have to assign here is actually 2 electron pairs. Right now, so we have to assign those 2 electron pairs to this one. Right, let's assign. So first we need to complete the octets of the cone atoms. Completing the octet means providing 4 electron pairs those cone atoms, right? So 1 is there, 2, 3, 4. 1, 2, 3, 4. 1 is there, 2, 3, 4, giving the 4 pair situation for those cone atoms, means providing the octets for those cone atoms. So all the 2 electrons have been allocated now, right? So after this stage, right, now we are not concerning about giving the octet for the central atom, because now we are with a third row or above central atom. So here we are not focusing on completing the octet of the central atom. Instead of that, right, we have to minimize the charges on this atom. We have to minimize the charges on this atom, right? Minimize the charge on this atom, right? So that we have to copy the charge of this thing first of all. Then only we are able to minimize the charge. So let's assign a charge of this one. these atoms there, right? So before the electronic movements, we have to we have to discuss about the charges here, not like the earlier case. Earlier case, we had done the electronic movement to complete the octet of the central atom. Now we are supposed to do the electronic movements to minimize the charges on the central atom, right? So that before doing the electronic movement, we need to come up with the charges on these atoms, right? So basically the central atom, right? So sulfur should have 6 electrons, but now you are with only 1, 2, 3, 4. 1, 2, 3, 4. 6 minus 4 means plus 2. The plus 2 is the charge of sulfur here. Oxygens should have 6 electrons as is group 16. Now we have provided 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. So all these oxygens are with minus 1. Some kind of same electronic arrangement. Right? So what we are supposed to do now? So basically, right, we have to minimize the charge on this sulfur. So for that, actually, we can give some electronic pairs from these atoms. We can provide some electronic pairs from these atoms. Let's see what will happen if you are to provide those electron pairs towards that atom. Let's see. First, locate one electronic pair to that space. Let's see what will happen with the movement of that electron pair. Let's have a good idea. So these are not changed. The electronic structures of those 3 atoms are not changed. No? 3 oxygens are not changed. No? So electronic structure of sulfur and oxygen changed due to this electronic movement. So let's assign the charges here. Let's assign the charges of these 2 guys there. Sulfur should have 6 electrons. Now you have only 1, 2, 3, 4, 5. Should have 6. Now you have 5. 1, 2, 3, 4, 5. That means plus 1. What about this? The oxygen should have 6 electrons. Now you have 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So that is how the charges distribute if you have to do this kind of a electronic movement. So with this electronic movement, you would clearly see what happened actually. The charge of the oxygen had vanished from here, and the charge of the sulfur had decreased as well. So basically, charge of the oxygen has decreased as well as the charge of the sulfur. So one can say like this. So electron donating atom. So this is the electron donating atom, right? These electrons are belongs to oxygen. The electron donating atom for the electronic movement, electron donating atom gets a positive charge. One can say like this. No? Electron donating atom gets a positive charge, while the electron gaining atom, this is the electron gaining atom towards the sulfur, the electrons are provided. Electron gaining atom gets a negative 1 charge, right? Electron donating atom gets a positive 1 charge, that is why it's become a 0. Electron gaining atom, right, gained the negative 1 charge, that is why the plus 1 is there. So if you can do another electron change, if you can do another electronic change like this will get a plus 1 charge. The electron donor gets a plus 1 charge, while the electron acceptor gets a minus 1 charge, so that the charge around the sulfur becomes 0, while this also becomes 0. So that is a good situation, right? That is what we are expecting actually as minimizing charges. So that is your SO4 2 minus. Right now, by doing this kind of electronic movements, right, we can minimize the charges on atoms. The electron donor atom gets a positive 1 charge, and the electron accepting atom gets a negative 1 charge. So if you are to do such 2 electron donations to the sulfur's plus 2 charge will vanish. Right? Okay. Actually, like in the earlier case, with this one also, the summation of formal charges should be equal to the charge integrity here. So summation of formal charges is actually minus 1, 0, minus 1, 0, minus 2, that is equal to here. That is done. So this structure can be acceptable, right? That is the idea. Let's do a few more 2 or 3 structures with this kind as well, where you have a central atom with a third row above. Let's try to draw a few more. Right? Okay, I'll draw a few more. Right? This is for 2 minus, no? It's clear, no? Right. Let's come up with few. Right. Let's draw for the let's come up with S. So 3 to no. Let's come up with some more. The PO for 3 minus. PO for 3 minus. Let's try to draw the structure of this one. PO for 3 minus. Right? So first the skeleton. So in drawing the skeleton, we have to consider the electronities. Phosphorus is 2.1, which is similar as the hydrogens. Oxygen is 3.5. So least electron atom should be at the center. So with the phosphate ion, phosphorus should be at the center. So other 4 oxygens should be connected like this. Right now? Right. Then do the valence electron count. PO4 2 minus. Phosphorus as group 15 element, it gives 5 electrons to the valence electron count. 5A element, right? 4 oxygens are there. 1 oxygen contributes 6 electrons each. Such 4 electrons oxygens are there. Then this kind of anion with 2 minus charge, that means 2 electrons added. 2 electrons added to the PO4. So altogether 16 electrons. 16 electrons. Sorry, PO4 minus, sorry for that. So PO4 3 minus, sorry for that. 3 electrons added. Right? So altogether 18 electrons. PO4 3 minus, no? Right. Electron pairs. 18 into 2 is 9 pairs. Then for the skeleton, 1, 2, 3, 4. 1, 2, 3, 4. 4 pairs have been used. So we have to deduct those 4 pairs. So 5 electron pairs are remaining. As lone pairs. Right, so we have to allocate altogether 5 electronic pairs. Sorry, we had done a wrong calculation here, no? See, 4 oxygens means here 24, no? Sorry, 24 and 24, 29, 32, no? Sorry, yeah, it should be 32. 32 electrons means 32 divided by 2 is 16. So 16 minus 4 is kind of 12 electronic pairs there, right? Let's assign 12 pairs to complete the octet of these, means providing the 4 pair situation for these cone atoms, right? So when providing the 4 pair situation for those 4 oxygen atoms, right? Now all the 12 pairs have been assigned, right? After this stage, we are supposed to minimize the formal charge of the phosphorus at the center. For that, first we need to come up with the charges. So oxygens should have 6 electrons, but now you have 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is minus 1. So minus 1 charge will appear with these oxygens. What about the phosphorus? Phosphorus should have 5 electrons as is the group 15. Now you have provided 1, 2, 3, 4. Then 1, 2, 3, 4 electrons for that. So its charge is plus 1. So this is the situation. So to get rid of this plus 1 and minus 1, right, you can provide you can move one of those pairs to here, right? When one of the pairs moves from here to here, what will happen? The electron providing atom gains a positive charge, so that this minus charge will disappear. Electron gaining atom will gain a negative charge, negative 1 charge, so that plus 1 will disappear, right? So ultimately the structure will look like this. So this is going to be your PO4 3- structure, right now. So summation of formal charges will be equal to what? The charge you get here. So this is your PO4 3-, right now. PO4 3-, okay. Let's come up with another one, right? Let's do another Lewis structure, right? Which is appearing with your note. See, let's try to draw the kind of a structure like SO2. Let's try to draw the SO2. SO2. Here also we are with a central atom, right? Which is with third row above. So sulfur atomic is 2.5, oxygen is with 3.5. So sulfur should be treated as a central atom, the central atom, right? So the skeleton comes like this. Skeleton comes like this. Sulfur at the center. So let's do the electron count then. Sulfur coming up with 6 electrons as it's group 16. 2 oxygens coming up with 6 electrons each as it is also group 16, 6A. So no charge there. So no need of adding or removing electrons. So altogether it is 18 electrons. What about the electron pairs? 18 into 2, that is 9 pairs. And for the skeleton, 2 is used. So as valence, as lone pairs, you are with 7 pairs. As lone pairs. Right now? Now, you should provide those 7 pairs to the skeleton. So what? So first completing the octet of the cone atoms. So 1 is there, providing 4 pairs situation for the cone atoms. 6 are used, and these guys octets are fulfilled as those are with 4 pairs each, right? So the remaining electron pair, the 6 are given, so 7 were there, right? Was there, so 7 should be given here. So that is how we are supposed to allocate the 7 pairs to the skeleton, right? After allocating the 7 pairs to the skeleton, we need to make sure that the central atom is with the least charges situation. For that, we need to assign charges, right? So let's assign charges. So oxygens, these kind of oxygens carry -1, right? So 6 electrons should be there, but you have 1, 2, 3, 4, 5, 6, 7. So this is also the same, right? What about the sulfur? There should be 6 electrons around sulfur. Now they have assigned only 1, 2, 3, 4. Only 4 electrons are assigned. That means sulfur is with +2 charge. Right? That is how it looks like after allocating the electronic pairs. So then we are supposed to minimize the charges on sulfur. For that, you need to provide 2 pairs towards the sulfur. So you can do so by this one as well as this one, right? So that as sulfur is gaining 2 electronic pairs towards that, it will come up with -2 charge. So -2 charge and the +2 charge will cancel off. As these electrons are provided by these oxygens, the electron donors get some plus charge. So plus charge and -1 charge will cancel off the charge on the oxygens, both of the oxygens, right? So ultimate structure is going to be like this then. And you have a lone pair on the sulfur as well. So this is the Lewis structure of SO2. Right now? Okay? That is the idea. Right, so with this, we'll wind up at for today's lesson, right? So actually we have discussed about drawing simple Lewis structures, actually with one central atom, right? We had done discussion actually with two sections, right? First we have discussed about when you have a second or non-metal as a central atom, how to draw a simple Lewis structure, and then ultimately we have discussed about how to draw a Lewis structure when you have a third row or above element at your center, right? So that was the discussion for today, right? So we'll wind up this stage, and with the next class we will discuss about the stabilities, how to comment on the stabilities of these Lewis structures drawn, and the resonance structures, and ultimately we'll discuss about drawing complex Lewis structures as well, how to draw Lewis structures with more than 2 central atoms in a skeleton, right? We'll discuss about those things as well at the next class, right? For today, right? That's all for today, right? So let's find out at this, right? Thank you, and right, goodbye then. See you next week.